Hello. In this video, we'll continue working through section 6C. So we mentioned most of the main components of what we're going to cover in class on Monday, but we really need to get some good practice. There are definitely some computational aspects here. There's a chart that we're going to need to see how to use. And overall, there's just a lot of really interesting and useful information that goes with the normal distribution. So we pointed out what the normal distribution is, something that looks more like these lines, and also started to mention the variation that goes with each of these. This one's a little taller and narrower, so the idea here is that the data values are a little more clustered in the middle, but they still eventually spread out, but fewer and fewer as we get away from the middle. Here we've got that same setup, but not quite as high and a little bit wider in the middle. So these both still would cover that normal distribution, but that's just a little bit of the variety as far as the variation and the standard deviation would be concerned. But just a reminder, so the normal distribution is a symmetric, bell-shaped distribution with a single peak. So that's what we're really seeing here. And I just want to quickly mention, this idea of bell-shaped, a lot of people focus on that in the middle, but they miss this end behavior. This is not a bell. That is just a hill. And that's one of the aspects that is not a normal distribution. Because as we talk about this, most of the time we'll see they'll tell us information is normally distributed, and that'll give us the key as far as where we should go from there. But just to get a few extra points about the normal distribution, one aspect is that, well, again, we've got that mean, mode, median all lining up in the center, and we've got the symmetry on both sides, and this picture would basically still have that. But the idea of the normal distribution is there is no limits on above or below the mean. How far above, how far below. So a lot of the situations that use the normal distribution, they're things that come up naturally in nature. A lot of things like when we talk about human beings, height, weight, shoe size, intelligence, IQ scores, SAT scores, things of that nature, they almost all tend to be normally distributed. That we end up getting these situations when there's so many factors. So if we talk about something like height or weight, you have genetics, you have upbringing, you have diet. There are so many different variables and factors that lead to our overall height and weight, so that naturally a lot of us fall in that middle area. So for something like height, for men it's 5'9", for women it's 5'2.5". That's the average height. And most people are somewhat close to that height, a little above, a little below, but most of us are in that ballpark. But there's truly no limits. There's not like you can't be 7 feet tall. There are men who are 7 feet tall, but there's very few of them. There are men that are under 5 feet tall, but there's very few of them. But it's still possible that we can go to those very far extremes. So that's just a little information. And now just look down here, the normal shape. Ultimately, we want to look at this type of distribution curve, but a lot of these things start off with some sort of a bar graph or a histogram. So in this one, they're just giving us two sets of information. This one talks about population density. This one talks about the chest circumference of Scottish militiamen. What a weird topic. But this is kind of more of a natural situation. Population, you might talk about feeling natural, but there's a lot of clusters that tend to happen. So that's why if we just think about which of these would represent a normal distribution, well, this one, we can kind of fit that natural bell curve right over the top of it. It fits very naturally over those bars. Now, it's not exactly perfect, right? This bar, we look in the middle and these two are equal height. This one is higher than this one is, but it still has that very similar picture. So that leads us to think that that should be normally distributed. Here, I'm going to be looking at something like this. We've got a couple little peaks, so just definitely not normal. Now, on the bottom of this, they give us a little bit more of that description. What does it mean to be normal? And that we see things like, again, they talk about height, they talk about a few things, and this idea of tailing off, that's that tail behavior that I was talking about. So the graph doesn't just come to an end, it just kind of slowly flattens and levels off. and gets closer and closer to the x-axis the further you go away. So now moving on a little bit, on a deeper level, again, the idea that there's just so many factors likely to follow a normal distribution. So that again, they talk about genetic, environmental factors. They talk about IQ scores. In sports statistics, things like batting averages tend to be normally distributed. So there's just really, we want to talk about an application section, something that gets applied in the real world. The normal distribution is very, very common. So they give us a few conditions. Now this is where I want to quickly move through this. This is another one of those places. It's nice to have some basic information, but we can't fully predict normal distribution. There's things that would seem a little more likely or a little less likely, but for the most part, we really do need to actually see some data to really be able to know that. But just to see, there are some conditions. Again, as we mentioned, most data values are clustered in the middle, near the mean, giving that distribution a well-defined single peak. It's not a guessing game, right? We clearly see one peak here. Over here, we've got a high peak, we've got another little peak, and another little peak. We've got a lot of little ups and downs. But in that normal distribution, it's that very simple. We go up to the peak, and then we come back down, and then we still have that nice symmetry. And that's the evenly spread around the mean, making that distribution symmetric. So we've got that mean in the middle, but that left-right action, we have that nice symmetry. Larger deviations from the mean becoming increasingly rare, producing the tapering tails. That's what we're talking about on the end. You can get very, very small. You can get very, very big. But most people are in the middle. And the further away, that's what they're talking about, the deviation from the mean. The further the data value away from the mean, it can happen, but it's increasingly rare. And of course, that again, a lot of times these types of distributions come when there's a combination of different factors such as genetic and environmental. So here's just a quick problem. Without any data, without looking at a histogram or something like that, can we tell which would be normal distribution? Well, scores on a very easy test, there's a lot of limits here. There's a maximum score. If this is a very easy test, we might expect a lot of people to be clustered near the top. So here's a perfect 100, here's an 80, here's a 60. Good scores, we'd expect a lot of people clustered up here, and then maybe we've got some lower scores down here. But there is an absolute cap on this top. And this seems like a situation that we might have. This would technically be called a left skewed. The heavy data on the right side, this would actually be a left skewed distribution. But I'm not so worried about that term, and this is what I mean. That's not an obvious thing to think about, but in the second part, the shoe sizes of random sample of adult women, that's again another one of those size factors. Height, weight, shoe size, hand size, head size, all those kinds of things. Very likely, because again, another one of those human traits that has a lot of factors. So a lot of quick information just to realize the normal distribution is really, really common. But now we can really jump in and see how that actually helps us. So this is where the standard deviation in normal distributions sets so much of the picture. Because we can have very, very different information. But as long as we look at things in terms of the mean in the middle and how many standard deviations above and below, we get a very nice picture that goes with this distribution. This, some books call this the empirical rule. Our book calls it the 68, 95, 99 rule, but it's really giving the same thing. So what is that rule? That rule, I'm just going to use 99. We don't need the 99.7. That's nice, but the 99 is enough. So what we get, about 68%, and this is a very, very close. This is not like about 68%, maybe it's 72%, maybe it's 60%. It really, really works out to be very, very close to 68%, or just a little over 2/3 of all your data falls exactly within one standard deviation of the mean. So going back up to this picture, this is what we're talking about. The mean goes in the middle. If you go one standard deviation below the mean to one standard deviation above the mean, you would get 68% of all of your data values would fall here. So this is what we're saying, again, in terms of height. And I think that's what we'll use as one of our examples. We'll do a quick one with height to point this out, and then we'll do a second example as well. But if we talk again about men's heights, 69 inches is the mean, okay? 5 foot 9 inches. And we have a standard deviation of 3 inches. So that means if you go 3 inches above, that would be 72 inches, to 3 inches below, that would be 66 inches. 68% of men would fall between those two heights. So that's what we keep saying. Most guys, if anything is normally distributed, most data values fall close to the mean. So here the mean is 5 foot 9 inches. Most men would fall somewhere close to 5 foot 9 inches. More specifically, 68% of men would be between 66 and 72 inches tall. That's how this works. But now we can also add in, I still have to explain the rest of the rule, but to just jump ahead a little bit, the symmetry. To get the full 68%, you've got to go down 1 standard deviation and also up 1 standard deviation. If you only go down, so if we only look from 66 to 69 inches tall, we would have half of this. It is a perfect symmetry. So if I've got 68% total, that would be 34% on the half below the mean and another 34% in the half above the mean. So that's going to really expand our tools here. That doesn't have to always be perfect, but we do need clean standard deviations here. So what I mean by that, from this type of information, using this rule, it's got to work out that the data values we're looking at are exactly a certain number of standard deviations above or below. So for instance, 70 inches would not work in this example. 70 inches is only 1 inch above the mean. I need to go in groups of 3 inches. So if I go 3 inches above, I get 72. If I go another 3 inches above, I get 75. Another 3 inches above, I get 78. Going down, subtract 3 once, I get 66. Subtract 3 again, I get 63. Subtract 3 again, I get 60. So these are the important height values we can use. And now continuing with this rule, 1 standard deviation away from the mean, you get the 68%. If you go 2 standard deviations away from the mean, so 2 full standard deviations below, 2 full standard deviations above, that's why they have that 95% here. And similarly, we can do above and below. If it's 95% total, half of that would be 47.5%. So 47.5% of men would be 2 standard deviations below the mean. 47.5 would be 2 standard deviations above the mean. And then similar, 99. Again, they really use, notice here, 68.3, 95.4, but it's perfectly fine to just use the 68.95. Not only is it perfectly fine, that's what I want you to use. I don't know why here they don't do that same thing. Stick with the 99 and then point out it's more precisely 99.7. So, point number 1. Go back to the standard deviation, that initial discussion, and we talked about most data goes from the mean minus 2 standard deviations to the mean plus 2 standard deviations. And we said back then that we would explain more why that is the case later on. Here it is. This is why we use that rule. Now you might ask, why don't we go out 3 standard deviations? That's unnecessary. There's so little outside there. You've got these tiny little regions that, again, the idea of most data, well, a little more than 95% definitely qualifies as most. So if we want to get a picture of how our data is spread out, that's why we use this as the general rule of thumb. So again, looking up here, using the men's heights, the average men is 69 inches tall. The standard deviation is 3 inches tall. So applying this idea, subtract the standard deviation twice, you get 63 inches. Add the standard deviation twice, you get 75 inches. And by far, most men are between 63 to 75 inches tall. So that's not easy, okay? Once we get into this, I've seen some people, they always want to draw this picture, but then as you get a little further along, you realize again the other aspects. If there's 68% in between these two heights, then you look at what percentage is left over if you go below 66 to above 72. And well, if it's 68% in the middle, that leaves 32% on the outside. 16% would be on this side. 16% would be on this side. So my point right now is that some people try and just draw this and apply it, kind of the way I did here, that every time they get information, they try and put all the important values, and then they try and fill all the percentages in, but then you just get this complete mess of a picture. What we really need is to be able to know how to apply each one of these. But it's always about 1 standard deviation from the mean, 2 standard deviation, or 3. And when we use these whole totals, that we're always thinking about both directions from the mean. So anything else, anything outside of that, will use this information first and then make the specific adjustments. So this is not easy, everybody. In your book, example 3, example 4, and even example 5. They gave you 3 good examples to get plenty of practice. We saw some of it here, but now let's go to a completely new situation. Let's write some information up, and let's see how we can apply this rule ourselves. So, let me make up a little situation here. I tell you, we looked at a bunch of college students and the number of text messages that they sent last week. We found the distribution was normal with a mean of 65 text messages and a standard deviation of 21 text messages. So far, just a lot of information. No question yet, just getting a lot of information. College students and the number of text message, we found the distribution was normal. Sometimes they might phrase that slightly differently, saying the data was normally distributed. But that is such a huge key that when we see that information, the data was normally distributed, the distribution was normal, that is really trying to almost scream out to keep in mind the 68, 95, 99 rule. So now let's get some questions here. Number 1, approximately, and the only reason I say approximately, just to go back here, again, that's the idea, the about 68%. So approximately, what percent of college students sent, what percent of college students sent between 23 and 107 text messages? So this is what I was just saying a moment ago. Some people, okay, they make the connection to the normal distribution. They're already thinking about the 68, 95, 99 rule, and they want to just start drawing and filling everything in. What I would suggest, get to the question. See the values that you care about. Fit them onto the bell curve. So I'm going to draw a quick bell curve. Remember, I'm not looking for perfection here, just something. This is a little not perfect. I could fix it a little bit if you make yours a little steeper. But that's, just to give me a visual so I could see and I could apply the rule. The 65 goes in the middle. I know a moment ago, I was putting these values across the top, but I typically put them along the x-axis. But they just had other information here, so I didn't want this to get too cluttered. But for me, now that we've got that specific, I want to start looking specifically at these values. What's the significance about 23 text messages compared to 65? Well, it's fewer than the mean. How much fewer? Again, make the connection. Realize there's got to be a connection between the mean and the standard deviation. So if I do 65 minus 21, I get 44. That's not the number we care about. So let's try it again. If I subtract 21 again, I get 23. That's the value we care about. I subtracted the standard deviation twice, so 23 is 2 standard deviations below the mean. So with that in mind, a lot of people are already jumping here, but remember, we've got to see specifically the idea of falling within 2 standard deviations. It's got to be exactly 2 standard deviations below to exactly 2 standard deviations above. So let's continue. We saw the connection between 23 and the mean, that it is 2 standard deviations below. How about 107? Well, 107 is bigger than 65. How much bigger? I'll add 21, and I get 86. Still not there, so I'll add 21 again. There's the matching 107. And in the same way, notice it's not random that I'm adding or subtracting 21. 21 was given as the standard deviation. And as we said in class the other day, I looked in the book. I thought they might stick one problem in where they wanted you to go through the whole formal process, find the mean, find the standard deviation, then ask you questions like this. But no, every problem I saw in the book, they do it just the way I did here. They gave you the information was normal. They provided you with the mean and the standard deviation, so you could kind of just get right to work. So there's got to be that connection. That's what I was saying here. I can't use 70 inches when the mean is 69 and the standard deviation is 3. I mean, later on there are tools to do that, but in this stage, and we're not going to get there, by the way, again, we're getting close to the end of our work with statistics. So for us, we're not going to worry about that. It's got to be increments of the standard deviation. So I was adding 3, I was subtracting 3, but it was all about 3 because 3 was the standard deviation. So that's what we've got here. I went 2 standard deviations below to 2 standard deviations above. This is exactly the second rule here. I know some people look at this as 3 rules. Really, it's 1 rule with 3 cases, but however you want to phrase it, this is the big one that we just used to answer this first question. But let's keep going. Let's get more practice to go along with this. So let's look at number 2. Just for space, everybody, basically the same question. I'm just going to jump to the end. So approximately what percentage of college students sent between 44 and 65 text messages? Same situation, start fresh. Don't look to this picture, make a new one. Think of it as a fresh problem. I'm gonna get my bell curve set up. See, this time I drew it much smaller and tighter. Again, I'm really just trying to use it to set it up. Am I below, am I above? And thinking about how many standard deviations. Here, 65 is in the middle, because that's still my mean. We're still using that same initial information. But that actually is one of my values. So we're getting this here to here situation, and here this was below the mean, this was above. We specifically found how many standard deviations. Here, this one is the mean. So let's just focus on this one. I'm just going to go right here and notice 44 is 1 standard deviation below the mean. But I'm not going 1 below to 1 above. I'm just in the below portion. So it's easy to say, okay, we're definitely using this rule, but 68% would be here to here. We're only looking at this portion. we're looking at half of the 68%, which would be 34%. All right, keep going with this. Like I said, definitely want to get some practice. And by the way, Monday's class, both the main topics, this and we're going to get to the standard score in a few minutes. We want to get some real practice with this. So you could already anticipate you want to get some practice on your own, but in class on Monday, we're definitely going to do quite a bit of this work to make sure we see all the little cases and that we're prepared for any situation that's presented to us. So let's keep going. Number 3, again, same thing. Approximately what percentage of college students, this time let's do sent more than 86 text messages? Okay. Now it feels like we're definitely in a different area. The previous couple of problems were all given two values. So we're trying to use this rule and find the significance of these values. Here, the idea of more than 86, we're uncapping the top end. We're going anything bigger than 86. So let's still draw the picture. 65, again, mean still not changing. What's so special about 86? We only got one value here, but let's still do the same work. And starting fresh, I mean, same thing. It's bigger than the mean. How much bigger? It's 1 standard deviation bigger. So just one quick point. If we come back here, and if I said 44 to 86, 44 is 1 standard deviation below, 86 is 1 standard deviation above, so 44 to 86 text messages, that would give the full 68%. But we only did the one side. So here, a couple ways to think about this. We know, similar to what we did here, from here to here is the 34%. The full 44 to 86 would be 68%. Here we only did the 1 standard deviation below, so we had half. Here is only the 1 standard deviation above, so we get half. So here's where we have to do some good critical thinking. We want this region. See, the previous ones, having the two boundaries, we're always looking in the middle of the graph to some extent. Here, now we're looking on the edge of the display. If I said less than 86, we'd go from here all the way over. We'll do that in just a second. But more than 86, we're looking at this region right here. So how do we figure this out? Well, a couple of things. Some people look at it that the whole thing has to add to 100% so that the entire left half of the curve is 50%. We know this region is 34%, so that these three regions are going to have to add to 100%. So we could see that these two combine to 84%, but we want the leftover. So take the whole 100% minus what we see on that side, and that would leave us 16% over here. Some people, a slight different way to do this, they never even think about the left side of the curve. They're just already thinking, okay, I want this, I know this. Well, completely ignoring the left half, the right half has to be 50%, right? 50% of the values come below the mean, 50% come above. So let's just focus on the above portion. I know this little gap, and again, this is not exactly proportional to try and figure out by area, well, this is half of that. No. Just trying to use it for a frame of reference that this covers this portion, this covers the total, so how do you get this? Similar, 50 minus 34, and we get the same answer. So I'm not trying to confuse you here, just trying to point out how you see things. It's not that we have to see it the exact same way. We can still get the same answer, but to realize we are using this rule, but at the same time, we are taking advantage of the symmetry and taking advantage that everything has to add to 100%. So just quickly to point out that if this was less than 86 text messages, well, now we'd be looking for this region. And as we kind of already saw, I know from here back to the mean is 34%, but I need this other entire half of the curve. So just to take what I have here, what I know is 34%, and what I know here is 50%, and to just add those together, and we would have 84%. Okay, last problem I want to do here. Again, I know this is not easy. This is a very tricky thing to get used to. There's a lot of numbers floating around, but to keep track, which are the data values, how many standard deviations away from the mean, and then using the graph to figure out what region you actually want. So definitely take some practice. Do the examples in the book, get into the homework, so that way, again, on Monday, you can make sure you've got all the tricks up your sleeve, and we could just make sure that you get good practice to go with it. Okay, I still just want to do one last one here, okay? We've seen how we can get percentages. So let me go to my next page here. And again, the reminder, we already know that the mean was 65 text messages and that the standard deviation was 21 text messages. This is kind of a part B, okay? In number one, actually let's do number two. In number two, we already found 34% of the students, approximately 34% of the students sent between 44 and 65 text messages. Everything the 68, 95, 99 rule gave us was based on percentages. So now let me just tweak this question a little bit. What if I said, in a group of 150 college students, how many, approximately, how many would have sent between 44 and 65 text messages? It's been a little while, but we saw this type of question way back when we were looking at the graphic displays, the charts, the different, graphs and all that type of stuff. We had a few of those questions. If we know the percentage and we know the total amount, percent out of the total group would give us the how many. But this is one of those situations we'll see. Sometimes it works out nice and clean, sometimes it doesn't. This one actually I think does work out pretty clean. We get a perfect 51. But this would be, again, this is literally college students. So if we got 51.2, we'd round that off. So here we'd have about 51 of the students sent between that many text messages. Okay, so good work so far. Again, not easy. The actual arithmetic we do is not tough, but it's a lot of bouncing back and forth, data values to standard deviations to the 68, 95, 99 values, and then using them appropriately. So now, wrapping things up, we want to finish with what we call the standard score. A lot of other books, especially statistics books, tend to call these z-scores. So that's why you see, why do they have this z, the standard score or z-score? And once again, they don't really use formulas, but let's do it ourselves. We use x for the data value, we use x bar for the mean, we use s for the standard deviation. So the standard score is actually a very, very simple formula. But in a moment, you'll see what we use this for. But the whole idea, it's literally figuring out this top part, the data value minus the mean, you get the total distance, the raw distance between these two values, and dividing by the standard deviation. Well, just notice something quickly. Go back to that previous example. We had the mean was 65, the standard deviation was 21, and that one of those problems, we had x was 44. If we figure out the z-score, 44 minus 65 divided by 21, we get negative 21 divided by 21 is negative 1. And similarly, just picking another one, let's look at when x was 107. When we had 107 text messages, the standard score for that number of text messages, you do your arithmetic, you'd get 107? Yeah. We'd get 42. Oh, yeah, that's right. 42 divided by 21, and we get 2. Why am I showing you this? Well, very quickly, just trying to show how we apply the formula, and they've got several good examples here, and to realize they're not always going to work out as perfectly clean, so we'll do a little bit of that work ourselves as well. But the first thing is to point out, what the heck is this z-score? What is this standard score actually telling us? It's looking at each individual data value and giving its value as far as how far away from the mean in terms of standard deviations. So 44 had a clean score of negative 1, and that corresponded with being exactly 1 standard deviation below the mean. 107 had a z-score of positive 2, which corresponds to a data value that is exactly 2 standard deviations above the mean. So we are seeing a little bit of connection. I don't want to make this too strong of a connection between the 68, 95, 99 rule, but there is some overlap here. Just to initially just try to establish what is the point of these scores. Now, why do we care about these scores? As we said in class, one of the main reasons for the standard score is a way to compare individual data values across different sets. So that's going to be the first one we do in a moment. We're going to look at 2 students' test scores, but test scores in different classes. And we'll see, not just to compare them straightforward, because we shouldn't, they're taking different tests, but to compare their performance based upon how their peers did. That's where we're ultimately going. And then what we can do with this, once we have the standard score, we'll see how we can use this table to talk about how a standard score corresponds with its percentile. The idea of the percentile, the percentage of data values that are less than or equal to it. So if you are in the 90th percentile with regard to test taking, that means you did better than 90% of the other people who took that test. If maybe you're a weightlifter and you're in the 90th percentile in a particular grouping, like maybe your bench press is in the 90th percentile, that means your bench press is better than 90% of the other people who bench press. Okay, that's the kind of situation. Okay, if we talk about, height, if you're in the 90th percentile for height, that means you're taller than 90% of the other people. So that's how this value works. And the connection is the standard deviations, that in every single normally distributed set, we can figure out those percentiles by figuring out the z-score. So let's combine all this. Let's see how all this works and comes together. So on my paper here, so that way I don't have to keep flipping back, I'll recopy that z-score formula. And let's just try and see how we can use this again. So let's look at 2 students. We have Jane got an 82 on the chemistry test. Billy got an 86 on the English test. Now, I'm leaving some space because we're going to fill more in, just to realize it's easy to just say, oh yeah, Billy did better on his test than Jane did, but to get extra context, this is where I'm technically comparing these people to each other, but I really want to compare by saying who did better compared to their peers. So I ultimately do want to compare Jane and Billy, but not by comparing their raw score on the test, by looking at how well they did, again, compared to their peers. So if I told you on the chemistry test, first, all test scores were normally distributed. That's not always the case, as we pointed out. Earlier we mentioned that easy test, and the likelihood that would not be normally distributed, but there's still very oftentimes, plenty of times, test scores do work out to be normally distributed. So let's say we had normally distributed, and the chemistry exam, we had a mean score of 84 with a standard deviation of 3. And then for Billy, on the English test, the mean score was an 83, and the standard deviation was 2. Well, very, very quickly, now all of a sudden compared to their peers, should be kind of obvious, Jane did lower than average compared to the rest of the class. Billy did better than average. Billy comparatively did better. So we could see that with their z-score. For Billy, his z-score, his grade minus the average grade divided by the standard deviation, you'll get 3 divided by 2, which is 1.5. So he did 1.5 standard deviations better than average. For Jane, she got an 84. She got an 82. The average score was an 84, and the standard deviation was 3. Just using my information for each individual class. An important note here, you don't get to pick. It's not big minus small. It's data value minus the mean. So here the data value was bigger than the mean, hence we ended up with a positive answer. Here the data value is smaller than the mean. I get negative 2 divided by 3, negative 0.6666 forever, so I'll just round that off, negative 0.67. So the fact that it's negative, we did worse than average. She is 0.67 standard deviations lower than average. So with that comparison, now just from their z-scores, well, a positive z beats a negative. Because a positive z is better than average, a negative is lower than average. We could conclude Billy did better compared to his peers. And here his peers would be his classmates. But what if it wasn't quite so obvious? This is a situation, how do I want to phrase this? Since one was better than average, one was worse, we could have just, without the z-score, still have come to that same conclusion. So now let's just go back and make a change. Let's go back down here. And let's say the average score on the chemistry test was a 77. Actually, let's make it a 75. Billy did better than average. Jane did better than average. You might try and do the raw totals. Well, he only did 3 points better than average. She did 7, but this has a higher standard deviation. So basically, there's no clear answer right here. The way to do this is to go through and do the z-scores, the standard scores. So I didn't change anything for Billy. So he still is 1.5 standard deviations better than average. But now let's fix Jane. With that new information, she still got an 82, but now the average score is a 75, and we still have the standard deviation of 3. So I get 7 over 3, and that'll be positive 2.333 forever. So now with that information, she did a little more than 2 standard deviations better. He did 1.5 standard deviations better. Now we would have Jane did better on her exam compared to the rest of her class. That's how a z-score can be really helpful as a comparison. So this, we did some tests. And in class, we'll do another one like this. I'll probably do something that compares completely different work fronts. Because here, this still feels like we're still comparing something sort of similar. But if we start comparing something like a factory worker and how much he does on the assembly line compared to a salesman and how much he sells, I mean, now it feels like we're almost talking about two completely different things. But they're still both workers, so we could still try and compare them in a way, and we would compare them by seeing how well they do compared to their peers. This guy packs more boxes on the assembly line. This guy sells more product than other salesmen, but we need the Z-scores to be able to distinguish who ultimately does better compared to their peers. So I'll save that example for class. For the rest of this video, let's come back and see how we use this chart. I've got to be 100% honest. I'm not a huge fan of this chart. There are, stats books, they use things like this all the time, but the one thing that bothers me is the way they set up their Z-scores. If you have Z-scores less than -1 or bigger than +1, you have to round off to the nearest 10th, and that's how you get the appropriate percentile ranking. If you have Z-scores that are from 0 up to -1 or from 0 to +1, now they want you to round to the nearest 0.05. I mean, that is not a natural thing we've ever been taught to do. So I really got to point that out right off the bat. That kind of bugs me. So let's see what we got for both Jane and Billy, okay, as percentile rankings. And this would be the same thing. The Z-score was enough, but to actually put a percentile rank next to it and see how this chart works. We still have to compute the Z-score. So for Billy, we got 1.5. So I would go right here on the chart. And this one is perfect. There's no rounding here. This worked out to exactly 1.5. So I go right here on the chart with 1.5. His percentile rank, he did better than 93.32% of his classmates. That's how we should understand the percentile rank. So he did really good. He did better than 93% of everybody else, so that's pretty darn good. But now when we come to Jane, 2.33, do we go here or here? We round to the nearest 10th. So we'll round this to 2.3. And 2.3 has a percentile rank of 98.93. So now you could really see both people did really well on their tests. He did better than 93% of his classmates, but she did better. It's basically 99% of her classmates. So looking in terms of percentile rank, it's not always a comparison, by the way. Some of the problems are just literally, what is the percentile rank for Billy, for the different situation. But I also want to make this clear that this is a very nice way to compare. By looking at the percentile rank, we could see even more clearly she did better compared to her class than he did. But let's do one more. Okay, let's start from scratch. Let's just literally do the problem as find the Z-score and its percentile rank. So I'm just going to give us some information. X is 41. X bar is 50. S is 3.5. Just so we can get used to the computation and using the chart. But very quickly, just to point out, remember, all of this, everything is still tying together with this idea of the bell curve. That this whole idea that if you're in the mean, you're better than 50% of the people who are below the mean, but lower than this 50%. So the mean has a 50% score, has a 50 percentile rank, I should say. But if you're below the mean, you're going to have less than a 50%. If you're above the mean, you'll have greater than 50%. So thinking about that, if you're exactly at the mean, you get a Z-score of 0. And 0 has that exact percentile rank of 50. Look at all the negative Z-scores. They all have percentile ranks less than 50%. And if you have a positive z-score, that your percentile rank is over 50%. That all still is corresponding based off of that normal distribution. So just seeing that this is below the mean, I know I'll get something lower, but let's actually do the work for it. 2 steps, 41 minus 50, enter, divided by 3.5. Now we've got a round. Negative, and this is more common. The previous, we had the 1.5 worked out perfectly. Sometimes, we've got the repeating decimal, but it's just we got to deal with it no matter which way. Here, we're specifically being asked for its percentile rank. So again, looking, well, negative 2.5, negative 2.6. I'm looking at one of these two. So round appropriately. If it's negative 2.57, we'll go to negative 2.6. 5 or bigger, we'd round up. And 2.6, we'd be in the 47th percentile. Oh, I'm sorry. Whoa, I read that wrong. Very sorry, everybody. Right? These are decimals. Look at that. We are in the 0.47 percentile. Sorry about that, everybody. And this, again, everything still corresponds. Two standard deviations below, 2 standard deviations above. That's where most data values fall. If you have a z-score less than -2 or greater than +2, there's very little below you, or there's very little left above you. So that's what we just saw a moment ago with the 2.3. That percentile had barely anybody above her because she had such a high z-score. So yeah, just to be careful with that, everybody, this literally is the percentile. I accidentally started moving the decimal, but no, this gives me the percentile as it is. So let's do another one. Let's look at number 2. Let's look at x is 156. X bar is 153. And the standard deviation is 4.5. Z, 156 minus 153 divided by 4.5. So I get, this is where we are. And like I said, this is why I hate the chart. Here, we rounded to the nearest 10th because that's the best we can do with this chart. But now here, we can't just go to the nearest 10th. I've got to consider what is the closest. So I've got 0.666 compared to 0.60, 0.65, 0.70, which is the closest, and it would be this one. So this would have a percentile. So first the 0.666 repeating for the z-score, and then the percentile rank would be 74.22%. You're above the mean. Definitely makes sense we get something bigger than 50%. But again, just looking at the actual value itself, and this is what I hate, everybody. Most of these charts have it set up so you're always rounding to the first decimal point or you're always rounding to the second. But here, it's not even that we're rounding to the second. We're just literally trying to see, okay, I'm 600ths away from this. I'm 400ths away from this. I'm only 100th away from this. So I do find that a little bit annoying, but this is the chart we're provided, so that's what we have to get accustomed to. Okay, so I think that's very good work. Like I said, there's a lot of computational work here, and with all these numbers floating around, percentiles, data values, mean, standard deviation, it's very easy to just feel like you're just kind of randomly plugging things in here or there. So make sure you get the right practice so we could make sure we're on the right track plugging in, and also starting to get that extra understanding of what that information is telling us. We've got several different types of problems from here, and even though they're all somehow connected based on the normal distribution, still a lot of different ways we can phrase and put this together. So again, that means from Monday, lots of review. We'll probably just move forward a little bit into 6D. 6D looks a lot shorter, so probably next Wednesday, we'll wrap up 6D and do a review video, and then it looks like 2 Wednesdays will be that first test. Okay, everybody, keep up the good work. Let me know if you have any problems, and I'll see everybody on Monday.